Okay, so well, you're supposed to watch this video, say alongside or afterwards you watch the regular videos that I upload. Now, one of the things that we learned before spring break, we called it factoring. Um, and one of the goals in factoring, remember, was to express or convert sums into products. So let's focus on what we were discussing prior to this, which is quadratic equations. Now, quadratic means the highest power of x is, highest power of the variable, let's say, is 2. So for example, I can have x squared plus, let's say, 5x plus 6. Now our goal is to study this equation. Now this equation it looks kind of complicated. So let's start with a simpler equation, a simpler one. Let's say I call a function of x and I call it x squared. Now the question is, how does this behave? Now recall the motivation is, say, traveling of an object under gravity. Yeah, we said the distance is proportional to the time squared. So it looks something like x squared. Now we learned way earlier in the semester how to plot functions by drawing tables, right? So let's say I pick some values of x and I look at values of f of x. Pick -2, -1, 0, 1, 2. 0 squared is 0, 1 squared is 1, 2 squared is 4. -1 squared is also 1 and -2 squared is also 4. So what we observe here is a symmetry, which means whether x is positive or negative, for the same positive and negative values, we get the same output. Now if you were to plot this function, it looks like that. Okay. Now this shape has a name. It's called a parabola. So notice this point right here is 0, 0. What we say is that's the point where the graph touches the x-axis. Now it turns out that knowing the shape of x squared is sufficient to know the shape of any quadratic. So from here we can sort of draw a conclusion that all quadratics look like parabolas when plotted. They may not look like this, they could look like that, they could look like that, they could look like that, they could look even downward, but the general shape is preserved, which means there is some notion of symmetry in these shapes. Now parabolas are pretty useful. Even earlier, like way before modern mathematics, some important properties about parabolas were observed. For example, one very interesting property which also has an application is that if you have a mirror which is parabolic in nature, and if you throw light on this, so light is just parallel beams like that, then each of these light ray, after reflecting from this mirror, goes through one single point, always. And this point is called the focus. Now this is not true for, let's say, if you take a semicircular arc, yeah, or if it's not parabolic, this property is not going to hold, that any light ray focuses on one point. There's a very famous story, which is most probably a myth, which is where Rome was being attacked by ships, and they set up a parabolic mirror such that the focus was on the ship, and using the sunlight which was focused, the ships were all burned. So pretty famous story, but it's probably not true. One of the modern applications of this is flashlight. And so in flashlight, the reverse of it happens. Mainly, what's the application of a flashlight is to be able to throw light as far and as focused as you can in order to see in the dark. So what you do is you have, instead of a reflector, you have a parabolic head, and you place the source of light at the focus. So what happens is when it hits these surfaces, because remember, light just radiates outwards in all direction, because of the parabolic nature, they then become straight lines. So instead of having a very diffused source of light, what you have is a focused, concentrated source of light which are in straight lines, which is what you want in a flashlight. So flashlights have parabolic reflectors, so that you can have straight lines which you can use to view really far. So this is sort of like a development of this subject. Next video, I'll talk more about sort of tying this down to some tools that you learned in the regular weekly videos.